Welcome to the video that accompanies day one of our kinetics and equilibrium unit. I've put out all of the essential ideas for the unit, so we tackle a little bit of these today for the case of evaporating water, and then we cover the same ones in our day two video for a chemical reaction. So don't feel overwhelmed by seeing all three of these at once. Chemical kinetics is the study of the rates of chemical reactions. So previously we have talked about the fact that chemical reactions happen, the rearrangement of the atoms. We've talked about the energy involved in them, but we've never talked about the speed at which they occur. So that's what chemical kinetics is about. And this includes an understanding, I'm just reading this first essential idea. This includes an understanding of some factors that can affect a reaction rate to make the reaction go faster or slower. Temperature and concentration of reactants are the two that we'll come across in this unit. And we're also going to look at some graphs and the shapes of the graph and the conclusions that we can make from looking at the graphs. And lastly on here, it's that these principles apply to physical processes as well as to chemical reactions. And so that's why we're starting with purely the physical process of water evaporating. The second essential idea in here is for reversible reactions. Most any reaction that we've seen this year has just had a right-directed arrow, and that implies that it just goes all from reactants to products. That's not always the case. The first time we encountered that was for the weak acid in the acids and bases unit, and we saw an arrow that went in both directions, and so that implied that not all the reactant was consumed. So we're going to take a look at that. And then lastly, we've got this term equilibrium here, and that is when the concentrations of reactions and products are constant. So the reaction happens for a while, and then it achieves what we're going to call an equilibrium. And in the last day, day three of this unit, we'll discuss that it's better called a dynamic equilibrium, and we'll talk about why we insert the word dynamic in there. But we hold off on that part today. Okay, so there's our water evaporating. That was just to finish the page, but that's what we're going to look at more closely. And so what I love about studying the water going from liquid to gaseous phase is that it's very relatable. So even before the chemistry course this year, you could think about having liquid water and heating it up and causing it to become gaseous. And then we're also okay with the idea of starting with gaseous water and removing heat from the system, cooling it down, and then liquid would form. Interestingly enough, if we're adding heat to the system, so if we start with liquid and we're having to add heat to it to get it to turn to gas, then heat is entering the system. So this top one is an endothermic process. And what happens in the bottom reaction is we've got gaseous water and we have to remove heat from it. Now granted, we're actively removing the heat in order to cool it to get the gaseous water to condense, but the idea of heat energy leaving the system means that this is an exothermic process. And those questions will come up on your test. Those are a little bit of an energy aside to this unit. So we're interested in the rates of chemical reactions. So I've got 6 slides here, and this is to represent the evaporation of water. So when it starts out, it's all water in this open container. I've got 1, 2, 3, 4, 5, it looks like I've got 8 molecules of water. And then as time goes by, the water begins to evaporate. So I'm going to put in here T equals 0 in the very beginning, and here's T equals, we'll say 1 minute goes by or 1 unit of time goes by, and it starts to evaporate. And then we have another time unit go by, and more of the water starts to evaporate. What I'm noticing now is some of my slides got messed up, so I'm too far into this process now to start from scratch. So we're just going to cross these out and say more time goes by, and then eventually all the water has turned from liquid water to gaseous water. That's T equals 3. Now we talked a little bit about speeding the process up, right? Affecting the rate of this process. And so if we were to increase the temperature of the system, the evaporation process would have happened more quickly. So maybe instead of going T equals 0, T equals 1, T equals 2, T equals 3, maybe the same process, if the water had been warmed up, could have been T equals 0, T equals 1/2, T equals 1, and T equals 1.5. Or if we cooled the water and just kept this in a very cold environment, the evaporation process would still occur, but it would be much longer. So maybe it would be T equals 0, T equals 5, T equals 10, T equals 15. So we're seeing here that with this physical process that we have some understanding of, temperature indeed affects the rate at which the process occurs. And so we can make graphs of that as well. So in this particular unit, one of the chemist's favorite graphs is graphing the amount of the reactants and products over time. And so in this process, we have this open container. Evaporation is a process that occurs at the surface of the water. And so the amount of water in the container will decrease over time. The amount of gaseous water starts at 0 and will increase over time. But this will occur at a constant rate based on the fact that the exposed surface of the water to the surroundings stays the same size through the process. I've thickened the line in places as the liquid water decreases and as the gaseous water increases. I've thickened those lines just as discussion points. But more often than not, from the graph that you would see in the classroom, this is just going to be decreasing and then flattening. This is going to be increasing and flattening. But let's take a look at those bolder portions. This line is a negative slope through here. At this point in time, that's a negative slope. That's a negative slope. So that's the mathematical indication that we have decreasing amount of liquid water over time. And then it flattens to 0, which means we're all done and that the amount isn't changing with time. Similarly, with the gaseous water, at any time along here, we have a positive slope to that graph. So that's indicating that the amount is increasing over time. That's the amount of gaseous water is increasing over time. Now, what are we seeing on the right-hand side? We're seeing that this is an increased temperature. This is an elevated temperature reaction. Why do I say it's elevated? Because the process completes more quickly. That is a steeper negative slope to that segment, so in roughly half the time, all that liquid water evaporated. And in roughly half the time, the gaseous water went from having none to having the full amount. And then it flattens, and from there on out, you're not getting changing concentrations with time. Your glass is empty. Those amounts aren't going to change over time. Now let's bring in the idea of a reversible process. This evaporation of water in an open container was not reversible, but how do we begin our study of a reversible process? A reversible process is a process in which the conversion of reactants to products and the conversion of products back to reactants can occur simultaneously. And we first saw that with the weak acid in the acids and bases unit, but here's our familiar arrow that goes in both directions. This implies that you do have liquid converting to gas and gas converting to liquid. Let's look at some drawings for these. Here is a set of 6 slides. And so we start in the upper left, and we have just poured liquid water in a container, and we've put a lid on the top of it. That's what that solid black line segment at the top is. So at T equals 1, at T equals 0, we're just starting the process. We don't have any gas in there. Then at T equals 1, the evaporation process has started. We have 2 gaseous water molecules. At T equals 2, the process, we're now up to 3. So it seems that I could argue that it's slowing down a little bit, because in the first time unit, we had 2 gaseous molecules form. In the second time unit, we only had 1 additional form. At T equals 3, we now have 4 gaseous molecules. But at T equals 4, we've still only got 4 gaseous molecules. And at T equals 5, we only have 4 gaseous molecules. So what I see there is the evaporation process started, but then it slowed over time, and you ended up with an equilibrium where you had amount of reactants left and you had amount of products formed, and they weren't changing with time. So let's look briefly at what the graphs of those look like. They looked different from the open container graphs because the rate of the process is slowing down. So you start with losing a lot of liquid first, and then it slows a little bit, and then you get to flat. In the formation of the gaseous water, at first you're making a lot when the process first starts. But then as the container fills with gas, you are creating less new gaseous water, and then eventually that process stops. And notice that these are settling in on non-zero amounts. You have some gas and you have some liquid in the container. What you typically see in math books is not these thicker segments. They'll just present it as one graph like that, and you have to make your conclusions from there. What's happening in the bottom one is this is just occurring faster. So maybe we're doing this process with warmer water or in a warmer classroom setting. And so you're really making the gaseous more quickly. That's supposed to be steeper, and then it flattens out much earlier. This one's flattening out in half the time. The decrease of the liquid, you're losing a lot quickly, and then a little bit less per minute, a little less per minute, and then it flattens out. You get to the same end point, you just get there faster. So I'm at 11 minutes, so I'm just going to cut this short, but that is an introduction to our unit on kinetics and equilibrium, and it's all done through considering the evaporation of water. Thank you.